Hello class, my name is Elizabeth Jones and this is my final project presentation for ADTA 5560, Recurrent Neural Networks for Sequence Data for the Fall 2022 session. This is the first of 3 videos for my final project presentation. My series of 3 videos will cover the entire project report, including all these parts of the project. The first part of the project was finding a time series dataset. I used the Federal Reserve Economic Data website and found the Consumer Price Index in the United States for used vehicles. This numeric dataset is from January 1969 through December 2020. There's a few missing dates in the dataset from the 1960s, so I narrowed the data to 1969 through 2020. There's 624 rows of data with 2 columns representing the date and the CPI. The CPI value started around 30 in 1969, then increased to level out from 1995 through 2020 around 140. The average of all data points is 113. Now we're on to the second part of the project, building, training, and evaluating a simple RNN with sine wave data. The project uses a simple RNN because I'm using sequential data that's in order based on their values. RNNs are great for working with sequential data because of their chain structure. Sequential data has the characteristic of persistence that works like memory. In other words, memory uses previous information to prepare for the future. The first part of the project was to draw it out. The overall picture of the simple RNN for this project shows it consists of 2 subnetwork structures. The input layer feeds into the first subnetwork. That's the simple RNN with 50 neurons. And the second subnetwork is a feed-forward neural network with 74 neurons creating 1 output. There's 3 layers, the simple RNN, the feed-forward neural network, and the output. Here's another way to visualize the model, and here's a preview of some code I put in the Jupyter Notebook to show the layers. There were several steps to the simple RNN part of the project. First, I imported Python libraries and I imported TensorFlow with the sequential model and the layers for dense and simple RNN. Then I imported the Keras time series generator to produce time series batches for training and testing the model. Next, I imported the min-max scaler to pre-process and scale the data to normalize it into a range of 0 and 1. Next, I generated data for the simple RNN by creating a sine wave using NumPy and created a range X from 0 to 74 and divided that range into 1,110 values of data points from 0 to 1,109. Here's a picture with an illustration of that range. Then Y is defined as the sine of X and the X and Y values are displayed. Next, the sine wave of X and Y values are plotted. Then the X and Y data are placed into a pandas data frame. The X value is the index of the sequence of values and the real data is the sine values of Y. The first 5 values of the data frame is then displayed and I check the length of the data frame, confirming it is 1,110 to match the original data set. The next few steps were focused on splitting the data for testing. First, I split 20% of the data for testing, providing 222 data points of that original 1,110 data set. If rounding was needed, I kept that additional step here to round, which provided the same value of 222. Next, the original data was split by taking the original data set, subtracting the test length of 222 to define the variable of test start index of 888. Then I checked the defined test start index, which outputs the value of 888. Here's a picture of the original data set and what's going on with defining the test data. Then I worked on defining the data for training and testing. The training data was defined as data train and starts from 0 up to the previously defined test start index 888, but not including that value, so it stops at 887. Here's that picture from earlier that shows how the original data set is being split for training and test. The testing data was defined as data test and starts at 888 through the end at 1,109. Then I displayed the first 5 records for training and testing. Then I normalized the data to scale it into the range 0 and 1. I created the min-max scalar and then trained the scalar to perform a normalization. Next, the training and testing data sets were normalized. And after that, I created the time series generator instance. The length of the time series input sequence was set to 50 historical data points to predict the next one. The batch size was set to 1, and the training time series generator was defined. There's 4 parameters. That is the inputs dataset, the outputs dataset, the length, and the batch size. Next, the X and Y are defined as the sample input sequence and the predicted target. Then I flattened and displayed the one-dimensional array of the 50 consecutive data points that are used as the input sequence. Next, I displayed Y, which is what X predicts. Up next was building this simple RNN model. One feature was defined as N features. That's because there's only one column of sign values of index X that provides the features to train the model. The Keras sequential model is defined for the model. Then the first layer is defined as a simple RNN with 74 neurons and an input shape of the length of the input sequence of 50 and the N features, which is 1. Then the second layer of the model is defined as a dense, fully connected layer for the final prediction with just one neuron because the output is only predicting one value as the next point of the sequence. Compiling the model is next with the atom optimizer and the mean squared errors, or MSE, loss function. Then I displayed the model summary. The next tasks were to train or fit the model. 2 parameters are provided, and the first is the time series generator, and the number of epochs is the second parameter. 5 epochs were defined for the model, and here's a look at the training epochs. After training, the model's performance was visualized by loading the loss data into a data frame and plotting the points. The loss value dropped off quickly after the first epoch, and when the second epoch is reached, the loss is very close to 0, and then there's a slight increase at the third epoch, with the best result or lowest loss found at the fourth epoch. Then there's a slight increase at the fifth epoch. The lower the loss value, the better, and that's because the atom optimizer is working to minimize losses when training. The model was then evaluated with test data. I displayed the length, which was 50. Then I displayed the first time series batch of 50 data points. Next, I reshaped the input sequence with 3 dimensions. I used 1 as the input sequence. The length of 50 is next, followed by the number of features. This is going to display 50 values, and the shape was then displayed as 151. Evaluating the model was next. I declared an empty list for test predictions. Then the first time series batch for testing was retrieved as the last 50 data points of the training data set. The batch was then reshaped into a 3D array. Next, a for loop was created to predict for each batch. This was 222 due to the size of the test data. Then the model gets the value of the first element by adding the model, then getting the value of the prediction. The prediction is stored into a list of predictions, then a new batch is generated for the next iteration of testing by dropping the first data point of the current input sequence and appending the newly predicted value to the end of the input sequence, maintaining the number of time series steps at 50. The normalized scaled result is converted back to the real values and the true predictions are displayed. I displayed the data test values and confirmed it has 222 rows and 1 column. The true predictions are then copied into the data frame of the original test data and added as another column. The data test was defined as the true predictions from earlier, and a header was added with the name of predictions. Then data test is displayed with 3 columns and 222 rows. Then I visualized the model. The goal of testing the model is to identify the degree of the model's learning ability after the training process. There's a gap between the sine wave and the predictions, indicating the predictions are close to the true values, but over and underestimation is occurring. All right, everyone, that's the end of video 1. Stay tuned for videos 2 and 3 for the rest of the presentation.